Heyo. All right. Hey, 11.7 ratios of areas. I'm just going to use the book for this. All right. We're talking about ratios of areas, but specifically areas. Well, how about this? Let's first talk. What do you mean ratio of areas? Well, take a look at these two shapes. Here you have a dang it, why can't I think? Here you have a parallelogram. Here you have a triangle. And so we can find the area of each, right? Well, what do you mean by the ratio? Well, the ratio of the area for the parallelogram to the area of the triangle is just a quotient. It's just a fraction, right? And so the area of the parallelogram over the area of the triangle, we can replace those with the actual value of the area. Since it's a parallelogram, it's base times height. Since it's a triangle, it's 1/2 base times height. And we can replace those values with what's given, figure out the quotient, simplify. And so that means that the area of this parallelogram is, it's definitely bigger than the area of this triangle, but it's bigger by a ratio of 15 to 8. And if you type that into your calculator, what would that be, like 1 point, I don't know, 1.8, 1.9? Anyways, but that's what the ratio of areas are. And so next we want to talk, well, similar figures, they have something special going on if they're similar. Let me bust this bad boy out. All right, so if shapes are similar, right? So let's just use an example of two generic triangles, and what you know is that they're similar. Now, if they're similar, you know that the ratio of the corresponding sides are equal, which means that since this height corresponds with this height, the ratio of H1 to H2 is the same as any of the corresponding sides. For example, H1 over H2 equals the same thing as S1 over S2. Likewise, base 1 over base 2 equals the same thing as S1 over S2 or H1 over H2. And so there is a relationship going on. And so, if two shapes are similar, then the ratios of their areas have a relationship that's going on with the ratio of the corresponding sides. And we're going to talk about that relationship. That's the only thing really in this section. Anyways, let me call the area of this triangle A1, area of this triangle A2. And so the ratio of A1 to A2 is a fraction, right? I'm going to replace this with the formula for the area of this triangle, 1/2 base times height, height times base, whatever. And then A2 is 1/2 height times base as well. This one uses H2 and B2, right? And so the 1/2s, they cancel. Then you have H1 times B1 over H2 times B2. Now, I'm going to separate these into two fractions. Now, this is the same thing as H1 over H2 times B1 over B2. Now, because the ratio of their corresponding parts is equal to the ratio of any side of the corresponding sides, I'm just going to show you that H1 over H2 equals the same thing as like S1 over S2. And B1 over B2, because it's a ratio, the ratio equals the same thing as S1 over S2, right? And so since they equal the same thing, I can replace this ratio with S1 over S2. I can replace this one with the same thing, S1 over S2. And then the ratio of the areas is going to be, well, when you multiply these, that's S1 over S2 squared. And so therefore, the takeaway is if you have similar shapes, then the areas, the ratio of their areas is equal to the square of the ratio of any of their corresponding sides. And so if you were just given H1 over H2, you could find the ratio of their areas by just taking H1 over H2 and squaring it, right? You could just take any corresponding side. S1 over S2, we just gave this S just to mean like some generic any corresponding sides. These we gave them H because they're heights, right? They're altitudes. But anyways, that's what the theorem says. And so let's see, for example, let's see how can we use this then, right? Who cares, right? How could we use this? Well, suppose you have similar pentagons, all right? Well, if they're similar, then their areas have a relationship. The ratio of their areas have a relationship with the ratio of their corresponding sides. And so we could find the ratio of area 1 here over area 2 by just finding the square of the ratio of any corresponding side. And so S1, 12, S2 is 9, and if you reduce that, it reduces to 4/3. You can square that, and you get 4 times 4, which is 16, 3 times 3, which is 9. And so the ratio of the areas is 16 to 9. Does that make sense? And so there's a whole bunch of different applications and different types of problems. Let's see what this problem is talking about. That's pretty much the same thing. Let's see. What about this one? Oh, okay. This one's sort of working backwards. So in this one, you already know the ratio of the areas. The ratio of the areas of similar parallelograms. You need to know they're similar, first of all, to use this theorem that we're talking about. So the ratio is 49 of area is 49 to 121. So 49 to 121. And so if you need to find the ratio of their bases, right? Well, the ratio of the areas is equal to the ratio of the bases because these are corresponding sides. But it's equal to the square of the corresponding sides. And so we could solve for this ratio by taking the square root of both sides. When you square root this, you take the square root of 49, which is 7, square root of 121, which is 11, and you get that the ratio of corresponding sides is 7 over 11. Now, that doesn't mean that it doesn't mean that B1 is 7, and it doesn't mean that B2 is 11. I hope you hear what I'm saying. All it means is that the ratio of these two sides reduces to 7 over 11, okay? And so what you could say, if you had to, depending on the complexity of the problem, you could say that B1 equals something like 7x, and B2 equals something like 11x. And so these values, they're B1's not exactly 7, but it's some multiple of 7, and this is some multiple of 11. I hope that makes sense. I think that's enough. The rest of the problems you're just gonna have to kind of like figure out. If you have any questions, let me know. You'll find the homework in the assignment. Okay, bye.